So in this second lecture, I will now talk about stochastic transport equation and regularization by noise for stochastic linear transport equation, right? So we will consider a linear transport equation with a possibly non-smooth vector field B, and we will show that adding the so-called transport noise, this equation is actually gets well. So we will see what this is. Okay, I was just started writing, and I will continue writing. Nevertheless, some recap very quick about stochastic integral, and I will also add something classical but new for those of you who have not seen, who are not acquainted with the stochastic integration. So okay, I just wrote what the properties of the definition and the properties of the Brownian motion, which is a process, so a random path. You can think this as a random path with independent increments and Gaussian increments, which is in particular is a path which is continuous but definitely not differentiable, and there's kind of this typical simple path that has this form. And as told you, you can think of that also as you can actually think of the derivative of the Brownian motion as the white noise, that is a process with whose values are independent, right? And they are Gaussian centered and with this covariance matrix, right? Right. So it is actually not a process but a random distribution in time, right? Distribution in time. So it's yes. And you can also think of this, I didn't say yesterday, but you can also think of this as the scaling limit of a random walk. So you typically go left or right with probability 1/2 independent of any previous choice. If you scale this suitably, then you get back the Brownian motion, right? This is another way to see random walk. And then I talked about stochastic Ito integral. So when you have a Brownian motion and Y stochastic process, let me forget for a moment about adaptiveness. You have continuous path. Then you can define the Ito integral as, roughly speaking, the limit of Riemann sums, Riemann-Stieltjes sum, right? This limit exists in probability provided, okay, let's say Y has continuous path. This can be relaxed actually, but it's fine for us. And Y is adapted, which means that you cannot contain info on, let's say, the future time, right? This is needed, this is crucial to have this definition and then the Ito isometry. I mean, roughly speaking, this will always be the case, except perhaps in a couple of situations, but you can, so you don't have to care if you are not acquainted with stochastic integration, you don't have to care too much at this level about this adaptiveness, right? Okay, and if you can, this Ito integral enjoys this nice property, this is called the Ito isometry, that is the expectation of the Ito integral is 0, and the variance of the Ito integral is actually the L2 norm, time and omega, the random parameter of the integrand, okay? The square of the L2 norm. Okay, other property that we have seen, let me just recall, these are the Ito formula, okay, which is, yes? Yeah, sure. Yes? No, it's a property, it's a property. So these ones are properties. Well, technically, I'm actually, this is not completely precise in the sense that I should actually assume that this is actually finite. All right. No, this is still 0. This is still 0 because the Y, the point is this, this is, you can think as W dot in a way, that Y W dot is positive, can assume both positive and negative values. Okay, so that's why there is this cancellation, right? The only thing I don't have to look into the future, that's the requirement. Okay, so Ito formula, so when I have a process which has this form, the X equal to F dt plus G dW, okay, there are suitable assumptions which I'm not writing, anyway, they are most of the time satisfied here. So this has to be understood, of course, in integral form, so that is to say, xt is equal to x0 plus integral 0t of fs ds plus integral 0t of gs dws, okay? where the latter is an Ito integral. Then once you have these and phi C2, okay, then, okay, FG, they are adapted. Let me just write this, but adapted. Okay, let me remind that all of these are in principle stochastic process, so they are random path. Okay, okay, so this is yeah, the random path. If phi is C2, then what you have is that you can write the chain rule for phi of x, which is grad phi of x times dx, plus, and then you have the second order term, which is typical of the stochastic integration, of the Ito integral. Okay. Okay. This is in principle matrix values. That's why I wrote transposed here, transposed. But I mean, you can see that we are in 1D for the first, right? So this is okay. And then just a recap on stochastic differential equation. These Ito stochastic differential equations. So we want to find the solution generally of this equation. So yesterday I only have just a Brownian motion. I told you, okay, fine, you can view this as xt equal to x0 plus integral 0t of b of, sorry, s xs in ds plus, and then here I just wrote the t, because this was enough when you have just the additive noise. However, okay, for today and also for tomorrow, when we are going to talk about the Kreitman noise, we need unfortunately better something more. So I need to consider more general diffusion metrics here, right? So here, and these of course I understand as an Ito integral. And okay, I can put an initial condition. Let's say deterministic for the one can make it more general. Okay. And so here you have, of course, okay, I have to be careful about the dimension, so B has to go from 0 times RD into RD. This is a vector field. Sigma, in principle, can be matrix values. Okay. B times M, because then W, I can assume this to be an M-dimensional Brownian motion, right? This is now, okay, so the dimension matches. Anyway, you can think that M is equal to 1 for the sake for this talk. This is up. Okay. And now I just want to recap what I mentioned yesterday, perhaps the Cauchy-Lipschitz theorem, which tells that, okay, it basically goes like in the deterministic case. So if B is, say, and sigma, sorry now, is, let's say, an infinity of time, but doesn't really matter, so the point is they have to be Lipschitz in space with possibly linear growth. Okay, this means just at most linear growth, right? Then there exists a unique solution, okay, for any x. And here, for those of you who knows, so for those of you who don't know, I just mean, okay, there exists a unique process which solves this equation. Of course, one can be more precise for those of you who know about whether this pathwise uniqueness or uniqueness in law. Here, this is actually pathwise uniqueness. But for those of you who are not acquainted with stochastic analysis, I just mean I take Brownian motion on some probability space omega AP, right? With, okay, there is a filtration, but let's forget about that. And I can find a unique process X which satisfies this equation here. Questions so far? Yes. Yes, I could assume more generally. It's okay. Yes, yes. Okay. So let me now introduce also another object which most of people in stochastic analysis perhaps have seen, but even in stochastic analysis, not in some cases not much used, which is another integral, which is so-called the Stratonovich integral. Okay, so let me start with the W Brownian motion. Let's do it in 1D, and then, okay, generalization in any dimension is just what you expect to have matching the dimensions, right? And then let's assume that I have a process Y which satisfies, which is satisfy an Ito differential form for F and G adapted. Okay, this means that I can write Y in this form here, right, for suitable F and G. Okay, now I want to define another integral for the reason you will see in a moment. Okay, which I use, which is called the Stratonovich integral, and will be denoted by this circ here. Okay. Well, doing something similar as I do for the Ito integral, which is here, or there, right? So let me take again, okay, the sum over the I in a certain partition. I want to take the increment of the Brownian motion. Of course, I want to take the limit as the size of the partition goes to 0. But here now I don't want to choose the initial, the value of Y at the initial point, not only, right? But I want to choose let's say the mid rule. So I want to take the initial, the values at the initial point plus the values at the final point, average. Now, if everything were smooth, okay, so if W were smooth, then everything should converge to the same object, right? The SU integral would be the same. This is no longer true in this case, and this is going to be something which is in generally different from the Ito integral. And in particular, you can, it is well defined under this, you have to assume that Y is not just a general continuous path, but you have to assume this form, but okay, that's technical. The important point is that you have the, perhaps I can write here, you have two things to keep in mind about this integral. So first of all, the relation between the Stratonovich and the Ito integral. So the Stratonovich integral, right, will be can be written as the Ito integral plus 1/2, okay, then I have here GS ds. Okay. This is technically the quadratic variation, for those of you who know, between Y and W, okay, but doesn't matter. Okay. You can view also this as a definition, more or less, right? So you can say that this, if you don't like this definition here, you can say, you can take the Stratonovich integral as a symbol for the Ito integral plus this term here. Right? This is fine as well. And the other thing, and this is why the Stratonovich integral, why we will use this definition, okay, is the Ito formula for Stratonovich integral. Okay, this is actually as in the deterministic case. Okay. So, namely, what I want to say is that if I take, let's say, now I just write this for SD, for Stratonovich SD. So let me assume that I have a process which solves this equation, and now this has to be, this is the Stratonovich integral, okay. Once I have this, and I know that phi is, and I have function phi C2, then phi of x can also be written in this form, right, as d phi of x Stratonovich dx, okay, which is just a shorthand notation for d phi of x bt x dt plus grad phi of x sigma of x Stratonovich. Let me, okay, just for technical reason, let me forget about that. Okay. Okay, so you see here you have no second order term. Okay, that's why this is particularly, I mean, in some cases for transport equation it is convenient, at least as you will see, to work with the Stratonovich integral. Okay. Of course, I mean, there is a second order term hidden because when you write this as an Ito integral plus correction, then the second derivative of phi appears, right? So it's not that, I mean, not in contradiction with the classical Ito formula. It's actually the classical Ito formula for the Ito integral. Okay, questions? Yes. 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 Yeah. So if you modify, let's say y and w, but probably even one of two should be fine, you converge to this integral. As the Stratonovich one, yes. This is a kind of, this is called Von-Sakai approximation, right? So actually, for example, what you can do, if you want to solve an SD like that, what you can do is that you can regularize epsilon, then you solve, this is now classical, just the derivative, and you converge, so no Stratonovich, no Ito integral, just classical WT epsilon dot, and then you converge to this equation here. So that's why, yeah, you're right, actually, that's another reason for introducing this integral. I will not use much, but that's actually okay, yes? Yes. Good question. So you want to take, say, ys for some s in, this is the question? Good question. Well, I think, okay, I think you can probably write, no, I think you don't converge to the same value, it's exactly because, in general at least, because this one will not, so probably you can write, yes? Exactly, okay. And probably you can write this as a kind of sum between the Ito and the Stratonovich, because in the end, no, sorry, no, you're right. No, okay. Okay. Okay, just one last thing about, then we talked about, we come back to our problem of regularization by noise. So, you see here I've written, let's say the Stratonovich one, but one can do it also with Ito. I've written an equation which is driven by a drift V and something which is, has the following form, right? Let me now give a name to this, because this is particular, perhaps it's more kind of more suggestive, so to say. Let me give a name to this object here, okay, which can be understood rigorously in time as a distribution, okay. Okay, if let's say sigma takes values, sigma of x is in, let's match the dimension, this is in d times m, and w is an m-dimensional Brownian motion, I can also write this as a sum over the column of sigma k of x w t dot k. Okay, well, these are just the components of w dot. Okay. Okay. Now, okay, why I'm saying so? In particular, we can find that the expectation we can compute. Okay, let me say actually. Sorry, perhaps I should say something first. That is that this V is a Gaussian vector field, which is centered. Okay, this is Gaussian because this is deterministic, so this is a sum of Gaussian, independent Gaussian vector fields. Okay, this is actually a distribution, but let's forget about that. Okay, with covariance matrix. Which is given by the following formula, Vtx Vsy. Okay, in time, this would just be the Dirac delta. Okay. And in space, this is nothing but the sum over k of sigma k of x, sigma k of y. Okay. These are the column vectors. Let me give a name to this. I can call this qxy. Right? Okay, now you can take what you can do actually, okay. This okay, so you can generally so this is true for finite sum a priori from k to from 1 to m, but what you can actually do is that you can consider the case in a way, so can take m equal to infinity, you can consider an infinite number of driving noise, right? And what you can do is that in this way, this is can be proven. You can consider, okay, any, let's say, Gaussian vector field which is centered and white in time. Okay, what I want to say is that so, and with covariance, with space covariance, I have to cross a little bit with Q. Okay. Okay, so something that satisfies essentially this formula with Q. Okay. So you can think in a way that this equation here is actually an ODE driven by a Gaussian vector field. Okay, so this, I mean, this is just another way to see this this SD, right? But perhaps more appealing. Okay. Yes, yes. No, I mean, well, W dot means here, I means the distribution valued WT, exactly. DW is essentially, this is always a notation to mean an integral, right? Which is the Stratonovich one or the Ito one, depending on the symbol, right? Okay. Hope you can read. Yes. The sum is finite, okay, provided actually, okay, provided certain assumption, but which will be satisfied here, right? So when you can take him, I have to actually guarantee that the square of this converges, right? So that in a way that this converges when m goes to infinity. You're right. That's actually what I need to assume. But in some sense, so I can take a. So this is essentially this last point is just a matter of more or less notation, but it's just convenient to think sometimes as a stochastic differential equation as an equation driven by a Gaussian vector field, which is of course white in time. Okay. And the point is, when I take m equal to infinity, here I can basically, so whenever I'm given a Gaussian vector field with a certain covariance matrix here, let's say smooth, and this white in time structure, then I can basically what I said here is that I can basically find vector field sigma k and Brownian noise W such that, independent Brownian noise W, such that I can write my V as in the following form, right? So that's perhaps what and then I can interpret my sort of, yeah, I can interpret, and I can consider an ODE driven by this Gaussian vector field. Okay, questions so far? Okay. basically erase this. Okay. Okay. Now let me just come back to the last point of about regularization for ODEs, which is, however, already pointing out to the transport equation, right? Which is about stochastic flow. Okay. So yesterday we saw that if you take an ODE with a irregular drift and you add noise, you get this equation is regularized. Okay, so you get well-posedness, pathwise existence, and pathwise uniqueness. Now, what we want to ask with this, with what we are going to see, is whether we can say something more. So whether we can have a smooth dependence on the initial condition. Okay, that's what we would like to see. Okay, and this is the question that we are going to answer now. Let's first start with the classical theory of stochastic flow when the coefficients are Lipschitz. Okay, so let's consider. Let me very actually start with an ODE. Okay, just to make sense of the questions. Okay, I just consider x dot equal to b of t x t. Okay, yes. Okay, and now I want to start, however, at the equation at time s. So I want to consider time s with a certain initial condition small x, right? So to remember about the time and initial position, I will write this as superscript. Okay. And now, well, what you know from the classical theory is that if B is smooth, okay, then there exists a family. So the family of solutions form indexed by, let's say, initial time and initial position. They form a flow of CK alpha homeomorphisms. So what do I mean by that? This is classical, but let me state for any S less than T, X S T, okay, the map that associate to the initial position the flow at time t, okay, the values of the solution at time t, is CK alpha homeo or diffeomorphism, depending on K and alpha, okay, with, okay, let me write just here, x and x minus 1, yes, and there is, let me just say if I really need this one, no, yes, I need because okay, with x and its inverse, okay, and their derivatives, which are jointly continuous in the triple S, T, and X. Okay? Right? So roughly speaking, we are going to take different positions. Okay, we are going to see what. Okay, this is actually deterministic, so smooth, right? So, which is the position of the particle? Let me of the particle starting at different this x at time t. Okay, and this has to be, of course, is a homeo or diffeomorphism. This is homeo homeomorphisms or diffeomorphisms depending on the regularity on B, but anyway. And moreover, we have the so-called cocycle property. Okay, this is to say x ut composed with x su is actually equal. Sorry, here I wrote now. Okay, better I write in another the blackboard. Cocycle property. And it is x ut composed with x su. This is just x st. And in particular, of course, well, okay, for any s mu. Okay. This should be, I mean, it's perhaps a bit boring for most of you, but it's just a classical property, the classical flow of home or diffeomorphism property, right? Questions so far? Yes. On no, right? Sorry, here just so it depends on the. Oh no, sorry, you're right. So I didn't write. You're right, actually. No, okay, sorry. This is just a definition. This is just so the values of k and alpha depends on the smoothness of B, right? So let's say if B is C1, what you can expect that this is C0. Say C1, say C01. This is C01. More or less, it's kind of inherits the regularity of B. Okay. 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 And now we want to take the same question, but for the SD. Sorry, it's a bit. This part is a bit of. I know that today I'm going to talk about a bit of preliminary, which I need in order to talk about the transport equation, right? Okay. So this is dx, so I'm just going to consider this as d here. Here I'm just consider an Ito as d. One can do similar things for Stratonovich, but has to require one more regularity. And now I want to take care of the initial, again, I want to start here at time s, right, with the initial condition. Sorry, this is s, initial condition x. Okay. Now let me first assume that B and sigma are smooth. Okay. And then the question that we would like to answer is whether we have smooth dependence on x in a pathwise way. Okay. So what I mean by that is that can I fix, so remember this is a stochastic, this is a kind of random differential equation, think of this as a random differential equations, right? And now what I mean by that is that can I actually fix the random realization of my noise, okay? And can I say that if I start, let's say, with 2 points which are very close, for this fixed random realization, the path, let's say x and y, x t s x and x t s y, these are also very close. And can I also have kind of differentiable assumption and so on, differentiable results and so on. Well, here there is a technical point, which is the fact that actually, okay, the x is actually defined only up to a zero measure set, okay, and this zero measure set may depend on x. So the exact question is the following. Well, okay, perhaps I can even skip. This is a bit technical. Okay, let me just give the definition of stochastic flow. Okay, I say that phi map from ST, okay, times RD times omega from RD is a stochastic flow of CK alpha homeomorphisms or diffeo homomorphism. Okay. If solving DSD, okay, DSD this one, let me call it, I don't know, 1. Okay, if the following happens. Okay, well, for every omega, so this map takes as an input initial time, final time, or well, time t, initial condition, and random parameter omega, right? So for every instance, basically, of the noise, this one phi, let's say, stx into x of stx omega is a flow of ck alpha omeo or diffeomorphism. And moreover, of course, for every initial condition S and for every x, okay, phi of S, let's say the map, the process x t, which is given by phi x t omega, phi s t x omega, solves, is a solution to DSD 1. Okay. So I'm basically saying that this is so for each omega, this is a flow of homomorphism or diffeomorphism, and this is actually a solution to the equation. And now I can state the result, classical result, that if B and sigma are, let's say, Lipschitz, with the most linear growth, and let's say at infinity in time, okay, then let me just give some space because I need to say here, okay, I need to take also, I want to take also another case, which I will need, at infinity time with values in C1 alpha, x ling, okay, for some alpha in 0, 1, okay, then, okay, there exists a unique stochastic flow solving DSD 1, let me call this phi. Okay, what is the regularity of this flow? The regularity is the following. Okay, in this case here, I cannot. This is I can say that this is almost C1, 1 minus epsilon. Okay, homeomorphism. Okay, while in the second case, in the case where my coefficient is actually C1 alpha, this is actually 1 alpha minus epsilon, diffeo. Okay. So you see, so if you ask for the regularity with respect to the initial condition here, we are losing, we do not really match the deterministic condition because we are losing always an epsilon for any epsilon larger than 0. Okay, but almost, we are almost, it is almost like in the deterministic case. So if the vector field is Lipschitz, then we get almost Lipschitz homomorphism. If the vector field are Holder, then we get, are 1 alpha, then we get 1 alpha minus epsilon, okay? Dependence on the initial condition.
So what's the reason for this loss?
Yes, this is due to, so basically, let me just give a reference and answer to your question. So I think the best reference for this is the Kunita Saint-Flour lecture notes. Now a bit, I don't remember, they are in the 80s. The reason for the loss, which is in the strategy of Punitab, okay, but as far as I know, cannot be avoided. So it's that you need, in order to how do we, this is a stochastic process, right? So if you want to use, so what you can do is that you can do estimate of the form, this, let's say, phi of x minus phi of y to the power m, okay? And I can say by just a more or less classical argument that this is bounded by x minus y to the power, let's say, m, okay, let's say for the Lipschitz. However, this I can say this for every x and y, but in order to state that this is a flow of homomorphism, I should actually need to pass to have a supremum of x inside. So I should take, I can say, so I would like to pass from this to say that the expectation of the supremum x different from y of phi of x minus phi of y, let's say the Lipschitz property, x minus y to the power m, this is actually fine. Something like that. Right? So in order to bring the supremum inside, I cannot bring the supremum inside the expectation unless I use something like Kolmogorov continuity criterion. Right? So if I use Kolmogorov continuity criterion, then however I have always a loss of an epsilon. Right? The reason is this one. Yes. Yes, yes. Exactly. So the proof goes by like that. So I prove estimates like this, then I apply Kolmogorov, but when I apply Kolmogorov, I always have a loss of something, right? I can take any m so that the loss is reduced as much as I want, but I cannot avoid the loss. Okay. Okay, so now this, let me now give the final result about this stochastic flow, the regularization by noise result. Okay, let me now consider the SD dx bt xt dt plus dw t, and with initial condition x0, x, okay. Okay, say t larger than s, okay, here I should, sorry, s of course here. Okay. And now let me assume that B is only Holder continuous, C 0 alpha, so to say, C alpha, okay. Cx B, x bounded, and L infinity in time. Right? Okay, under this condition, we have seen yesterday that this equation has a unique solutions. Now we can say something more about the dependence on the initial condition. We can actually say that there exists a unique sort of phi stochastic flow solving the SD, let me call now Q, okay, which is of what? Is of C1 alpha minus epsilon diffeomorphism. Okay, so you have, if you want, you have a gain of almost 1 degree of regularity with respect to the initial conditions, right? Okay, why is that the case? Why is that the case? Well, the thing is, I don't want to do the proof right now, but the idea is that the proof is again based on transformation, on change of coordinate, change of variable. Okay. Transformation of SD that I showed you yesterday. Remember, with this transformation of SD, we transformed this original SD into a new one with a gain of 1 degree of regularity. Okay, and this is exactly what, and then we can invoke the classical result here. Okay, this one in this version here, and get this result here. Now I can finally talk about the stochastic transport equation. So regularization by noise. Okay. For linear transport PDEs. Okay. So, how familiar are you with the transport and continuity equations? Right. So have you seen, in the deterministic case at least? How many have seen? I mean, I guess most of you have seen, but is there somebody who has not seen transport equation or continuity equation? Everybody knows this? Okay, very good. So let me just perhaps recall this. Right, so so let me recap anyway the deterministic case. Okay. Okay, so we have on one side the Lagrangian description. Okay, so I have an equation x dot t equal to b t x t and x0 equal to x. Okay, which is the evolution of particles, and we have seen that this gives rise to a flow of homomorphisms or diffeomorphisms. Then we have the continuity equation. Okay, let's say we are always on time times Rd, which is the following equation: dt mu plus divergence of b mu is equal to 0, understood in the sense of distribution. This is the continuity equation. And okay, so the solution, so B is always a given vector field, B0t times Rd into Rd. Okay. Okay, and this represents, so mu is the solution. You can view this as a map, actually as a measure, but mu times Rd into R is the solution. And you can view this as the equation for the evolution of your mass. Right? So you take an initial profile, so to say at time 0, you let the Lagrangian, the OD evolve, okay, and you get, and you transport the mass through this X, okay, and then you will get another mass, another evolution, another profile of mass. Right? In more formally, I can say that if I take mu0 initial mass, then the push forward under the flow xt of mu0 is a solution to the continuity equation. Right. Okay. So this is exactly the mass at time t. Okay. Okay, then there is also the transport equation. Okay. Did I have space there? Or? No. I don't remember if. Oh, no, better I do it here. Okay. equation on, okay, so this is just takes the form of dt theta plus b times grad theta equal to 0. And that's the solution is again a scalar field. Okay, this is the solution. And this is the equation for the evolution of transported quantities. Okay, it is to say, if, let's say theta t composed with the flow, the solution itself is just constant in time. Okay, and so this is in particular theta 0 of x, right? In other words, this can also be written as theta tx equal to theta 0 composed with the inverse flow. Okay. Right. Okay, so if you want to have a picture, again, I think you have all seen these things, but so to recap, if you start with, let's say, two colors here, okay, then you follow at time 0, then you follow this time equal to 0, then you follow your path, and then you get, so let's say, for example, this is, I don't know, the value is theta equal to 1, and this is the value theta equal to 0, so to say, just to make an example. Okay, this is the transport equation describes the evolution of these transported colors, right? Okay, as a function of time and space x. Okay, now I want to go to do similar things in the stochastic case. So in some sense, sorry, this was kind of, let's say, stochastic case. Okay, so finally I can write the stochastic transport equation. Okay, let me first start, recall, perhaps I've erased the SD itself. This is just dx equal to b tx dt plus sigma t xt dw, okay, with initial condition x 0 equal to x. Okay, so this is the classical SD. Now we want to write an equation for the evolution of the mass and the evolution of the transported quantities for this SD here. Okay? Let us start with the evolution of the mass, the stochastic continuity equation. Okay, so this takes the following form: dt mu, then we have the deterministic term, divergence of b mu, okay, and then we have we expect to have something like the one that we see in the deterministic case. So this is the divergence of sigma mu dw equal to 0. Okay. Now, what's the right choice here of the integration, right? So, in order to get one thing that you have to keep in mind, that in order to obtain this to say that this is the evolution of mass, what you can do? What I can say, let me go back one moment to the deterministic case, right? If I just take this as a definition, I want the equation for mu, what I can always say is that I can say, okay, if I test mu against the test function phi, this is nothing but mu0 against phi of xt, right? And then, if I do so, then what I can, to get the equation here, I just apply the chain rule. This is just grad phi of xt times phi x dot, which is, however, bxt. And I can go back and obtain mu t grad phi times p. Okay? This is how you can say that this continuity equation is the evolution of mass for this Lagrangian description, right? So you see, here I've applied the chain rule, right? I want to apply, so this means that if I want the evolution of the mass in the stochastic case, then I have to apply the stochastic chain rule. Now, I can do this, I can consider the Ito integral, but if I consider the Ito integral, here I have a counter term, second order term. Instead, if I consider Stratonovich integral, the Ito integral, the Ito formula looks the same, and then I don't have other terms, right? So I didn't do any formal proof here, right? But okay, but at least I hope I convinced you that the right notion of the continuity equation is should be this one, right? At least if I use the Stratonovich integral, okay? Right. Okay, and similarly, I can write now the stochastic transpose. This, okay, let me just remark one point here. Okay. Right. So this describes, as I mentioned before, the evolution of mass associated with the SD. And this is the pathwise evolution. I'm not averaging over the noise, right? This is not a Fokker-Planck. For those of you, this is not the Fokker-Planck. So in other words, let me say, we can think that we have again an initial mass times 0, okay? And we let your system evolve, right? Okay. This is one possible evolution. So I'm taking, say, a realization of my flow, xt omega, let's say phi, okay, and then I get a new mass here, right? This would be mu0, and this is mu t at time. One thing that I should remark, and I should have written, sorry, the solution, this is now an SPD, so it's an equation SD with, let's say, involving a space derivative of the solutions, right? So it's stochastic partial differential equation, and my solution mu, at least formally, can be viewed as a solution, as a function, depending on time, space, are valued, and also the random parameter omega, okay? So for each omega, you have a different field, different scalar field. So this is, let's say, one scalar field. Of course, if I have another realization of my path, let's say this one, I don't know, okay? For another omega, let me call omega prime, okay? Phi t, phi t of omega prime, okay? Then I have another value, right? Mu t of, let's say, omega prime, another mass, another profile. So this is just to stress the detail, not averaging over the noise. This is the math. I'm just considering I'm fixing the realization of the noise. I'm considering initial mass, and I let the system evolve, and I want to see the evolution at time t. Okay. Okay. Similarly, I can consider the stochastic transport equation. Okay, now it should not look surprising to you. This should be d theta plus b times grad theta dt, and then I should have here sigma times grad theta Stratonovich dw equal to 0. Okay. In a similar way that you have here. And again, this is the solution theta is now a random field, so depends on time, space, and my random parameter omega with values in R. Okay, and this describes the evolution of transported quantities. Okay, these are also called passive scalars, right? So again, if you have here, okay, let me use just red and blue, but okay. So if I have here the initial condition, this form, and then I let the flow evolve, the red and blue are transported, so this should be red, this should be blue, should be blue. Okay, so this is red and this becomes blue. Time t, space x, right? More or less as in the deterministic case, except that now my paths are random and are irregular in time. Okay. Okay. So let me just, okay. So questions so far? So this was a bit heavy notation-wise, but there's nothing much, not some big concept so far. It's just because I need this to introduce the equation for evolution of mass, and the stochastic flow is the concept that I'm going to use in a moment to state a regularization by noise for the stochastic transport equation. Okay. Okay, so okay, now I can give, this would be, this probably was the first part I didn't put, this is a kind of, point one was the, kind of, let's say, definition. Now I can give the regularization results. Thank you. Okay, regularization for linear transport. Okay, now let me consider B, the transport equation which I just written. Okay, okay, let me first perhaps recall the, yeah, okay. And then let me add just the additive noise, right? So this is the transport equation for dsd dx b t xt dt plus dw. So here basically my sigma is just 1, right? And in this case, it doesn't matter here whether I put Stratonovich or Ito, because, okay, in this case, this is just, in integral form, this is just the Brownian motion, right? Here, however, I do have to put, to leave Stratonovich, right? Okay. Here is the following, now the result. Assume that B is only Holder continuous. Let's say bounded. Okay. Okay. Then, okay, sorry, I have to assume something more on the divergence for technical reason, for reason that you will see in a moment. This has to be in LQ plus, in time and space. The spatial divergence of B has to be in that class. Then, for any initial condition theta 0, bounded, right? Strong existence and pathwise uniqueness hold in the class L infinity, time, space, and also the random variable omega, random parameter omega. Let me call this S3 for the equation, the transport equation 3. Okay. This is due, this result is due in this form essentially to Franco, Flandoli, Max Cubinelli, and Enrico Priola in 2010. Okay, the same paper that I quoted yesterday. Okay. Yes. Yeah, absolutely, absolutely. So existence is in a way, well, actually, okay, yes, existence is not difficult and does not, you need very relaxed assumption. You just exactly. So linear. So this is a linear equation. Okay, this I should have mentioned, but these are all linear equations. Well, okay, well, you can. Right, so this is, so existence, you can just get it by, say, some compactness argument, right? In the linear case, yes. In the linear case, yes, because you can basically argue by, it is enough to have weak star, you can use basically the weak convergence, okay? Weak star convergence in L infinity. Since it is linear, this is enough to pass the limit. You don't have to control some strong convergence. Otherwise, it would not be, I agree. But okay, the important thing is pathwise uniqueness, of course, right? So this is also kind of historically was quite important result because it was the first result or one of the first results where one could show regularization result for the PDE, not just for the ODE, okay? Right. Yeah, okay, so then the important, yeah, so this is not true in the deterministic case, in particular, let's say for, again, if you take the usual drift, b of x equal to, let's say, x to the power alpha, even in 1D, so to say, yeah, okay, x to the power alpha, like sine of x, okay. For alpha positive, this is not. This equation is going to have more than the PDE itself. The transport equation is going to have more than one solution, right? So this is not. This is a regularization result, right? Okay. So okay, since then there have been many improvements, right? Based both on these techniques and on other techniques, but let me just stick with this because it fits well with what we have seen yesterday and what we have seen in the previous part of these lectures, right? Okay. Okay, so let me now try to give an idea of the proof in the remaining time. As I was just mentioned, the important part is uniqueness, so I will just focus on uniqueness. Okay. Yes. Yeah, you're right. Right. Here I can ask. I think I have to ask. Let me think about for a moment. I think I have to ask here alpha larger than 1/2 to fit, if I'm not right. But yeah. So it's yes to fit this result. Otherwise, I can consider. No. Yes. You're right. No, yes, it doesn't. I mean, this is not really a strict assumption. In a way, there are now even more refined results you can do better. You can consider B, which is unbounded, right? So it's again, there is a large, as we saw before yesterday, there was a larger class LP-LQ, and you can have a similar result in LP-LQ as well. QLQ time LP in space, right? So this is not the most general result in a way, but this is kind of the one that it fits in the frame. Okay, so let me go step one. Okay, so this is the idea is essentially one. The idea is that this is the transport equation for the SD, this one, right? And this one, we know that it has a unique solution, and we know that it has a nice flow, right? Now, morally speaking, this is not always true, and I will comment about that. But when you have I mean, for me, at least morally speaking, when you have uniqueness for the OD or for the SD is morally related, is morally linked with the uniqueness for the corresponding transport or continuity equation. Okay. At the technical level, one has to be careful, and I will show this in a moment. But morally, the idea is this one, right? Okay. So let's now make this link precise. So let me say the idea is. So idea, okay, use link between SD and stochastic transport. Okay. Okay. Why exactly what we want to show? We want to show rigorously the transport property. So that if I take the solution theta and I compose with the stochastic flow x t, this is just going to be constant in time. In time, yes. And in particular, of course, it has to be theta 0x. This is immediately allowed to conclude because this says that then theta tx, I can invert this flow. Sorry, perhaps I should write here x tx is the flow, stochastic flow, solving the SD. That's why I introduced all this stochastic flow, which was a bit heavy, but in the end of the story, that's why we are going. So theta tx, then I can invert the flow, and I can say that this is just theta 0 xt minus 1 applied to x. Okay, so I will be a bit sloppy in the notation. I will use sometimes this notation. This is also this notation here, and the inverse flow will be denoted by often by this, right? Right. Okay. So, once I show this, I'm happy, and I can conclude the uniqueness to the solution. The solution is has to have this form, right? If I can say yes for any theta 0 initial. Okay, so let me now do the first step. Okay. Now, in principle, okay, when you want to show this is constant, I just would like to take the time the derivative of this and show that this is 0. Okay. Okay, here this is a stochastic process, so instead of taking the time derivative, I take the differential, and I would like to apply it to a formula, right? I would like to apply it to a formula to get the formula for this one. Okay. However, I cannot do it because theta a priori is just a bounded solution, right? So what I can do is try to regularize the epsilon and apply the Ito formula to this one, right? So where theta epsilon is theta convolved with some approximation of the identity, the kind of the same that we saw in the first lecture yesterday, okay? And try to apply the formula, right? So what I get here, how much time do I have? Let me check. 10 minutes, okay. I think I can still show something. Okay, so what I get from here is the following. So let me apply to, so we are in the Stratonovich framework. The nice thing of the Stratonovich framework is that Ito formula looks the same as in the deterministic way. So this is Stratonovich d theta epsilon dxt. Think of this as a time derivative, okay? Okay, plus grad theta epsilon dxt Stratonovich dxt. Okay. Now this one, because it satisfies the transport equation, This one would give us b times grad theta, but of course this is convolved with rho epsilon, txt. Okay. And then I have also minus grad theta convolved with rho epsilon, Stratonovich dwt. Sorry, here I forgot the dt. This is the first term here, the one that comes from the transport equation. Then I have the terms coming from the dx. This would be grad theta epsilon, okay. Grad theta, sorry, here I forgot, of course, txt. So I have grad theta epsilon times b t of xt dt. This is the drift coming from the equation for x, and then I have the Brownian motion, grad theta epsilon txt Stratonovich dwt. Hope you can read. Let me know if you cannot, right? Okay. Now, luckily, these two terms are exactly the same, because this is just grad theta convolved, this is just grad theta epsilon. Okay. But the deterministic drift is, they're not going to give the same result, so let me just write it here. This is not going to give me the following term. Okay, this is b times grad theta epsilon convolved with theta txt. Okay, where this is what? This is nothing but, sorry that I have to change. So this is nothing but a commutator, b times grad rho convolved with theta. This is nothing but b times grad rho convolved with theta minus b times grad theta convolved with the rho epsilon. Okay. Of the similar form, yes. Okay. Yes. Yes, yes, exactly. So yeah, so yeah, perhaps I should have done this. Where the point is where? Let me. Yes. So this is just obtain. It works exactly in the deterministic case because there is just a convolution in space. So I can just say this is d theta epsilon is just equal to b times grad theta convolved with theta epsilon. Okay. Of course, here, okay, here I have to, sorry, there is a minus here. I have to make sense of this. What I can do is that I can bring this on the either on divergence of B or on the grad epsilon, so that this makes sense even for theta just bounded. But this is just in the deterministic case. And then I have plus, let's say, grad theta convolved with rho epsilon, Stratonovich dw. Because this just depends on time, so it does not. Okay. Yes. It works essentially as in deterministic case. There is, I guess, a minus if I write this. Okay. And then when I apply this to this one, then I get. Think that this is just for this computation. Really, think that W is smooth in time. It does not change, right? Because the Ito formula for Stratonovich integral allows to do this computation here as well. Right? This point is, I'm not using the noise here. This is just this one here. This is I pushed things a bit under the carpet. So this is essentially this is the Stratonovich. Okay, because this is actually okay. The thing is, this is actually should be an Ito-Wenzel formula because here not only this is stochastic but also this is stochastics, right? So if this were deterministic, where it was smooth in time, this I would have d theta epsilon, right? If I right, and so if I would be then if you think that let's say W is smooth, then I would have this formula here. Now, this is not true because this is not deterministic, and what's worse, this is actually not smooth in time, right? But you can also have a formula, an Ito formula in this case, and you have to replace the time derivative here with the Stratonovich differential, right? And when you do so, you get the first bit here. Anyway, really, for this kind of computation, things, not for what I'm saying in a moment, but when you apply the stochastic chain rule in the Stratonovich integral, you can basically think that W is a smooth path, right? This is called also sometimes Malyaven transfer principle. So whenever you have a computation which is done for the deterministic case, you can add the noise provided you do in Stratonovich form. And the same computation at the level, computation using the chain rule, the same holds true in the stochastic case, right? So just think that here everything is smooth, W is smooth, whatever, right? And then you get exactly exactly this one. It will be works as well, right? Okay, so far, in fact, we have not used the noise. This is just completely deterministic. And this is the commutator similar to what we show. It's not exactly the same, but it's similar to what it was used yesterday in the Danchan-Robert paper. Okay, and now this is very familiar to people that work in transport equation as well, Di-Pernalions, Ambrosio, and so on. So, okay, now the step 2, of course, to conclude the argument, we would like to show that B times grad rho epsilon convolved with theta, so this commutator T xt goes to 0 in a suitable form. I just need this in distributions. Okay. Let me, for the computation here, now assume for simplicity the divergence is 0. Okay. Otherwise, there are other terms, but it's not, does not really too more complicated. Okay. Okay. This in particular implies that my flow preserves the Lebesgue measures. Okay. Okay. Now, let me try to give, I will not do all the computation also for time restriction, but let me show things, the idea. When I use this notation, by the way, I used more than one, sorry, I should have mentioned before. Here I mean when I write, let me even write, no, let me write here. Fg, this is just the L2 scalar product, right? So it's Fg in the X, in space. Okay? And here, this is a function of X through this, through the flow, right? Okay, now what I can do here, so I want to use so this will not go to 0 in general, right? Otherwise, even the deterministic equation would be, the deterministic transport equation would be always, would be well posed, right? But this is not true. So I have to use something, either the regularity on B, but this is not the case, because again, if I would be, this would be true also in the deterministic case, or the regularity on the flow X. So what I'm going to do right now to use that is to change variable and to basically invert, transfer the X from theta, from the commutator term to the test function. So phi is just a test here. Phi is smooth as much as you want. Okay, so this is going to be theta phi xt minus 1, inverse flow. And I don't have any Jacobian just because I assume this. Otherwise, I have a Jacobian, I have to control that, but let me forget about it. Right? And now, okay, let me just skip the passages, which, however, are in the same spirit of what we saw in the first lecture yesterday. So you can write this way. Okay. Just going to finish in a moment. Okay. Now you see I'm trying to bring the derivative on this term here. Okay. Now, and here you see why it is the theory of stochastic flow was relevant. Okay. because I know that this term here, okay, phi is smooth, so I don't care. I care. This is actually C1, C1 alpha even, but C1 alpha minus epsilon, but in particular is C1. Okay. So the reason why, this double integral will, sorry, this is dx, no, dx is at phi. Okay. This double integral goes to 0 is essentially because I know how to control this term here, because the flow is, because the dx is a flow of homeomorphism, is of diffeomorphism, sorry. Okay, and this is where I use the noise. This is the point where I use the noise, because of the noise. C1 in X because of noise. Okay, actually C1 minus F. Okay, and if you want the full estimate, this term here is bounded by up to a constant. So here you get factor, so B is C alpha, so this is epsilon to the power alpha times Z to the power alpha. Okay, well I can even not write it fully, it's, you can see from here. This is I'm going to get a factor alpha, which I like here. This one is bounded, fine. This one is just integrable, smooth, and so on, so will not create problem. This one is under control because of the C1. This is going to 0, right? Okay. And yeah, sorry for the delay. I just want to say perhaps one short comment. I used to think that in the end, the uniqueness of the SD is related to uniqueness of the transport equation, right? This is true in the deterministic and the stochastic case, Maurelli. Although to make this rigorous, you need something, always something more, some regularity more on B, on the solution, or something, or the flow, and so on. Nonetheless, there have been constructed some example of non-uniqueness situations when, for very wide solution, by convex integration techniques, right? I think that Stefano Modena will going to talk about that in next week, right? So I'm not an expert, I don't know. So this was why perhaps it's better I don't say something wrong about that, but this is also a nice point. Okay, thank you. Sorry for the delay. A space-time noise, you mean? No, okay, sorry, okay, yes. So what I can say is that I can always take, okay, this is not done in the paper, but I think there have been other papers. I can take these things, right? Let me say Stratonovich, just because not to make things. And as soon as sigma is elliptic, so let's say I have this condition here, for lambda larger than 0, okay, perhaps bounded because you want. Yeah, so okay, so you want something like, yeah, okay, let me say, you want something like, yeah, yeah. I agree, but okay, if sigma is, so you are, I can write, recall I can write this, of course, as a generic, like Brownian motion with this, let's say I can write this way, if you like, right, this term here. So I can allow for a general sigma, okay, as long as sigma is smooth, okay, and is elliptic. Smooth because, as you said, if I do this computation with a general sigma, I get extra commutator, probably even second order because I have the, but then if it is smooth, I can use the smoothness of sigma to make this 0, okay? I need this condition here because this is the one to the, I mean, so if you go back to the SD, right here, sorry, here, of course, here, if I have this should be this one. If I go back to the SD to have that the regularization by noise result is true for this sigma, I need sigma to be, I need to have non-degenerate noise. There are now even results about degenerate noise, like Ormander type condition that one can ask for. One can do much more than that, right? So this was just kind of, of course, I mean, when sigma is too irregular, okay, this is Krajknan noise, and the behavior is quite different. We will see this hopefully, yeah, in the next lecture. Okay. Yes.
If I understand correctly,
Yes, exactly, exactly.
The uniqueness of the PDE.
Yes, yes.
Now that seems to me, strange, because in the deterministic sense,
You do the other way.
well, not just that you go the other way, but we have situations where there is a well-defined flow, regular Lagrangian flow, but there is no uniqueness for the transport equation.
Okay. You mean, and do you have uniqueness of the, yes.
And the clue, I mean, the reason that can happen is that having a regular Lagrangian flow, capital X, amounts to saying that if you have, if you consider, uniqueness of the transport equation in the class of bounded densities,
Yes.
you have uniqueness. But the counterexamples you referred to by Modena, these ones are with unbounded density.
Yeah.
So I don't know, I'm missing something.
So, okay, do you refer, okay, I'm not an expert about this results.
I think it's that, it's
yes.
the regularization where at some moment things are very close.
Yes, yes.
And then you're saying things are bounded in the next way. But that's the place where the Debayan is a similar.
Yes.
But things are not bounded. It's the integrability that fails, not the
okay. Okay, so, okay, first of all, okay, I may miss something as well. Not the result is true, but there is one thing that one has to be careful about whether I consider continuity or transport equation. This is also, so here what I'm using here is the fact that, okay, the way that I understand the results by Modena is that if you go below certain threshold of integrability, then you lose the transport, the uniqueness property of the transport equation. So you can have kind of solutions which are unbounded. This is something that I cannot exclude here from here. So here I've stated the existence and uniqueness in L infinity. Don't know exactly. So there might be in principle, okay, there are more general results, but there might be unbounded. So do you think that, so okay, you are.
So the result is saying that you have uniqueness in the class of solutions which are bounded.
Exactly.
A priori bounded.
Yes.
It's not okay. So you could have other solutions.
Yes.
The same bounded initial data which are unknown.
If I remember correctly, there is even a paper which deals with similar things, right? Okay. Okay, now I don't remember the assumption. No, perhaps this is outside the Krylov-Lochner class. So okay, I'm not sure. But in principle, there can be something like that, right? Thing is, I'm saying that among the bounded solution for which you know that there exists a solution, then there is uniqueness. This is something I can say, right? Yes. You say if I change the domain, no, I would say, okay, when you take a domain, okay, let's say on the torus you can do the same, right? If you take a domain with boundaries, okay, and on manifold without boundaries, it's just slightly more, I mean, the computations are longer, so you have perhaps commutator in the sigma because you cannot just take additive noise in the SD itself. But it works the same as long as your noise is moves in space, right? Okay. With boundaries, I guess the only perhaps there is a paper, I don't remember, but what one should care is just that your vector field are parallel to the boundary so that you are not exiting the boundary, which actually might now create problem. Okay. Okay, no, this I'm not sure. Okay. Sorry?
Did anybody do it?
Sorry?
Did anybody extend this?
I remember a paper by Vladimir Neves and Christian Oliveira, which deal with transport equation in a bounded domain. I don't they get something, but I'm not sure they get such a strong result, so strong in a sense, such a result, so to say. So this I don't know. Okay, I have to check. I have to check.
we take a break and